Hey there, students. So what I've got for you here is a problem from the third section, our final section of chapter 9. This specifically is number 40 on the homework number 12 problem set. So in the first two sections of chapter 9, we were comparing values between two populations, proportions, means, things like that. And so those are situations where we took a sample from one population and we took a sample from another population, and they might have been different in size. And then we took the mean values or looked at the proportions from each of those samples. Whereas in section 3 of chapter 9, the two different values from the different populations are paired together in some way. For example, you might have spouses, so you have two different groups, but they're connected individually because they're married. Or maybe you have values from, as we do in this problem, values from your left hand and from your right hand from a bunch of different people. So one population is the values from the left hands and one population is the values from the right hands. But they're paired together because you pair up the values of the left and right hand from the same person. So I'm pointing this out because part of being able to do problems from 9.3 is to recognize when it is a problem from 9.3, when the two different sets of values are paired together in some way. Now, if you're doing a problem from 9.3, you're going to kind of know that because that's what we discuss in that section. But, if you're doing a midterm or a final or something and the problem just pops up and you don't know where it came from in the book, if you have two populations that values are being drawn from, you have to recognize from the description of the problem whether the values are paired together or not. And so the comparison to make here is that, for example, if you have two different population samples and then you take the mean of one and the mean of the other, and then you compare them by taking the difference, well, then you've taken the difference of the means of the two samples. Whereas if you have samples and all the values in one sample and the other are paired together, then before you take the mean value, you take the difference of every single pair, and you actually get a bunch of differences of those pairs. And then you take the mean of the differences. And they're going to ask you that in this problem. So that's why I'm explaining it. And so, yeah, we want to be able to go into the problem and after reading the problem, understand whether the different values from the populations are paired together. All right, so let's look at this one. It says, several students were tested for reaction times in thousandths of a second using their right hand and their left hands. Each value is the elapsed time between the release of a strip of paper and the instant that it is caught by the subject. Results from 5 of the students are included in the graph to the right, and they show us this graph here. Use a 5% significance level to test the claim that there is no difference between the reaction times of the right and left hands. So they give us the data from these samples as well as in the graph, also in this table. And then in this table, we can see that we can open it in StatCrunch. And so when they make these columns like this is part of how we can see that it's possible to have these paired together. So if I open this in StatCrunch, then what we see when it's in StatCrunch with these two columns is that you could have two individual samples of data, and maybe they're paired or maybe they're not. We don't know just from the fact that they're in the StatCrunch this way. But if they're paired together, then each row would represent the pair of values that were paired together from the two different groups, in this case, right-hand values and left-hand values. And so we need to know from the problem if it's paired together or not, and then we need to tell StatCrunch whether they're paired together or not. So how does this work? It says, what are the hypotheses for this test? So the symbol we use when the population values are paired together is mu sub d, because we're taking the mean value of the differences of the pairs versus getting the mean of each sample and then taking the difference of the means. So they ask us to choose which of those is going on here. Is it the mean of the differences or the difference between the means? When they're paired together, you take the differences first, then you take the mean of the differences. When they're not paired and you have just two different piles of numbers, you take the means of the numbers, then you take the difference of the means. So difference between the means is when they're not paired, and mean of the differences is when they're paired, which is what we're doing in 9.3. And in this case, each right and left-hand value is paired together because they came from the same person. So then our null hypothesis is always about equality. And so our claim would be that the mean of the differences of the pairs is equal to 0. And then our claim here is just simply that there's no difference, not that one is faster than the other or one reaction time is less than the other, but just there's no difference. So that means the alternative claim would be that it's not equal to 0, and that our claim is the null hypothesis here. All right, so having answered that first part, they then would like us to get the test statistic. So I want to get the test statistic. Now, they've given us a little indicator here that it's a t-value, so that's helpful. We are talking about means where we don't know the standard deviation of all the differences. So that's a t, but if we didn't remember that, it says t equals, so we know it's a t-distribution. So I'm going to go over to t-stats. So in chapter 8, we did one sample. In chapter 9, whoops, go back to t-stat. Get there again. T-stats. In chapter 8, we did one sample. In chapter 9, we did two sample in the first part. But now in 9.3, we have paired values. So that's our third option. We have to go t-stats paired. Then when they're paired, they know they're going to use the rows to pair the values together. So they say select the column for your first sample, which for us is the right hand, and the second sample is the left hand. Now, I'm also going to point out here that I don't think we need it for this problem, but it is possible some of the problems want you to work with the differences between these. StatCrunch will calculate those automatically, but if you click on this little thing here where it says differences, I recommend you just do that. Then when StatCrunch does its business, it will also make a new column and show you what the differences were, all those values and their differences. So then our null hypothesis and alternative hypothesis by default are what we set up for this problem. So I'm going to hit compute. And now when I do compute and I get my little results box, I'll point out that notice the differences have been tabulated in this new column called differences. But for the moment, all we need is the t-stat. So I'm going to grab that number to 3 decimals. I don't want to mess up my midterm, so I'm going to try to make sure I do all this correctly. So the last digit is an 8, but it's followed by 6, so I need to round it up to a 9. Yay. Okay, so now they want the critical value. So you may recall that the critical values are the alternative way of doing a problem as opposed to the p-value. So some of these problems will, after the test statistic, will ask for the p-value, and if they do, it's sitting right there in the results, and that's usually the simpler, easier way to go. But in this case, we have a problem where they ask for the critical value, and remember, the critical values are based purely on the significance level. They don't have anything to do with the sample. And so we don't use this information that we had here. Instead, we need to use the t-distribution calculator. So let me go grab that. So I'm going to go to stat calculator t for t-distribution. So here's the t-distribution calculator. So then we can use the significance level to try to find out where the critical t-values would be with a significance level of 5% being in the critical region. Now, to do that correctly, we need to know, is this a one-tailed test or a two-tailed test? When we have the alternative hypothesis of being inequality, that means we have a two-tailed test. We're going to have critical regions counting on the right and left tails. And that means we want the 5% significance level to be divvied up equally between the two tails. And then that critical region will contain 5% altogether for both tails. Now, because of that, it's not the default on the calculator is a one-tail test. So I'm going to go to between, and now I have two tails. And in the between, we need to enter in the degrees of freedom, and we need to enter the area in the middle. So we only had 5 values here, so our degrees of freedom is going to be 4. And then for both of the tails to add up for 5%, then the middle region has 95%, and we have to enter the middle region here, the part between the two critical values. So I'm going to go 0.95 and hit compute. And so it shows me a picture where 95% of the data is in the middle. That means the other 5% is split between the two tails, and that happens between the outside of these two critical values. So they do give us a choice for a single critical value. That would be for a one-tailed test, or critical values where t is plus or minus a number. That's for the two-tailed test. That's what we have here. So I'm just going to take one of those values and put it after the plus or minus on part B. It says to do this to 3 decimals, so I'm going to throw away that 4 on the end, and then I should be good. So then based on that, we want to draw a conclusion. Again, if we were using the p-value method, which we can use because we have the p-value right here, we would see the p-value is 2.5%. The significance level is 5%. So the p is low, so we would reject the null. We would reject the idea that the mean of the differences is 0. And instead, we would think that there seems to be some mean difference between the two. But using the critical value method, because the test statistic is larger in size, or in this case, the -3.5 would put it over in this left-tailed critical region, since the cutoff here is at 2.7 and we're over at -3.489. So again, the critical value says how big the number of the test statistic needs to be to reject the null, and it is definitely bigger than that. So we would say there is enough evidence to warrant rejection of the claim that there is no difference between the reaction times. So this was number 40 from the problem set. Hopefully this helps, at least shows you how to use the tools. Keep up the hard work.